are over 1.5 billion vehicles on the road today that all have something in common: the essential intelligence of S&P Global Mobility. We provide invaluable information across the entire value chain, enabling vehicle manufacturers, suppliers, dealers and consumers to make decisions with conviction. Our proprietary data is used to set pricing, plan future production, determine demand, and accurately predict make and model preferences.
Hello everyone. A very warm welcome to 2022 Automotive Solutions webinar series. We are conducting this special one on supply chain crisis update, special focus on semiconductor, in order to alleviate fears on special demand, how to mitigate the risk owing to huge vehicle production losses due to semiconductor shortage, chip shortage. Before going any further, I would want to take this opportunity to wish one and all on this webinar a very happy International Women's Day. Let me now introduce Jeremy, who is the speaker for this webinar. Jeremy Boucher is based out of London and is our practice leader for electronics and electrical and semiconductor practice. He's a global leader for us. And myself, Mohit Arora, I'm a regional manager for supply chain and technology for S&P Global based out of India, Gurgaon office. We have received registrations from across the globe for this one, which is why we have live captioning in different languages. English will be the core mode of communication for delivery. While we have captioning in French, Chinese, Japanese, Korean, and German. IHS Markit is now part of S&P Global. From 1st of March, IHS Markit has ceased to exist, and as a part of global merger, we are now known as S&P Global. The process took almost a year, but now finally we are S&P Global. S&P Global is divided into 6 divisions. Let me call out each one of them. S&P Global Market Intelligence, S&P Global Ratings, S&P Global Commodity Insights, S&P Global Mobility, for which we are as automotive a part, S&P Dow Jones Indices, and S&P Global Engineering Solutions. A bit about S&P Global Mobility. What we do here is provide invaluable insights derived from unmatched automotive data, enabling our customers to anticipate change, make decisions with conviction. Our expertise helps our customers to optimize their businesses, reach the right consumers, and shape the future of mobility. A bit more on S&P Global Mobility. We are further subdivided into 3 sub-verticals: Carfax, Automotive Mastermind, and Automotive Insights. While Carfax and Automotive Mastermind are dealing with used car data and new registrations data, this delivery of webinar is from the Automotive Insights team, wherein we capture 30 million forecast data information points on a monthly basis. I will now call upon Jeremy and hand it over to you. Jeremy, please take forward.
Hello, Mohit. Thank you for the introduction. So I'm Jeremy Boucher, and it's my pleasure today to present our latest analysis on the chip shortage. So the chip shortage for automotive has made the headlines for over a year now, and we are still not out of the wood. So I'd like to present the latest here. So I will start with a first section showing where we stand today. Then I'd like to explain why we believe 2022 should be slightly better. And then I'll explain in the third part why we believe there will still be some issues, a structural supply constraints which will persist through 2024. Then we would like to explain as well what it means for the OEMs on how the OEMs are getting ready for this new normal with chip supply constraints. And then I'd like to also comment on the Ukraine crisis, on how it does possibly impact the semiconductor supply issues here already. Okay, so let me start with where do we stand today? And to answer this question here, I borrowed a slide from our colleagues from the Light Vehicle Production Forecast, which have been tracking the disruption in terms of vehicle loss due to the semiconductor shortage since the beginning of the crisis in January 2021. And we see here the total loss cumulated since it started here amounting to 10.3 million cars. So it's massive, as we all know. And we show it here by quarter, but also by geography, by region of vehicle production. And as you can see here, every region has been impacted badly. It's very clear. And what you can see here as well in the distribution by quarter is that the third quarter of 2021 in every region was the worst one. Q4 2021 looks a bit better. On Q1 2022 is not finished, but it also looks a little bit better. So it's a glimpse of hope here, but we need to be careful. Then I would like also to show a more linear evolution of this vehicle disruption, because it gives us some insights here on the various phases of this crisis since started in January. So you can see here, we highlighted it with this first red mark. We saw an acceleration of a crisis starting from March last year until end of May, early June. And this was related to two events which disrupted further the supply of microcontrollers, which were already the bottlenecks at the beginning of the crisis. So there has been a fire in one of the major fabs of Renesas, the #1 microcontroller or MCU supplier in Japan. And then a few weeks later, there was an ice storm in Texas, you may remember, and it has affected as well NXP and Infineon, which are also the next leaders for microcontrollers. So this was, you see how the number of vehicles not produced has increased here sharply after these events here. The second acceleration here we saw last year was more widespread by type of semiconductor. It was related to a wave of COVID lockdowns which happened in Southeast Asia. And one must understand the semiconductor fabrication is very concentrated. So the back-end processes, which are the packaging, the testing of the chips at the end of the fabrication processes, are largely concentrated in Southeast Asia, in Malaysia, Philippines, Singapore, which were badly hit here by COVID and lockdown. And you can see here again this acceleration of a curve here on of disruptions, and not only for microcontrollers, but for all type of chips. And then, which looks like a good news here is the orange line at the end. We see that the rate of vehicle losses has somehow slowed down here since November. It's still growing, but not as fast as before. So the industry and ourselves have been asking ourselves, okay, is it getting better? Are we getting out of a ditch? Or is it possibly that the OEMs have now integrated this disruption or these issues in terms of chip supply as part of their planification, and therefore they report less vehicle loss due to this crisis? So we think it's a little bit of both. And but overall, when you're listening to what the industry says, it's still confusing. We see on the one hand, on the left here, some quite positive, optimistic, or even bullish announcements from some OEMs, which sometimes make announcements as if there was no constraint anymore. So Toyota, for example, mid of December, they made this announcement that January would be a record in terms of vehicle production with 800,000 units. Then you see this article from Reuters here pointing out how GM, Ford, and Hyundai are very optimistic here for 2022. And then we also noticed here that in China, the vehicle production is actually on the paper doesn't look disrupted anymore here. So these are the positive announcements. On the other side, we see also some note of caution here. So some OEMs are more conservative or cautious, I would say, like Volkswagen, for example, which announced publicly that they expect that 2022 will be rather flat compared to last year, so not a massive jump. And then what we noticed as well is that several car makers, after making some very optimistic plan or announcements on their vehicle production for 2022, just a few weeks later, they had to cut their vehicle production forecast already. So for example, Toyota being affected here by chip shortage again, February, and then Ford a few days ago announcing here several plants which are halting production again. And then also a comment on China. While you may have seen on 2 slides before that China seems not as affected anymore, we need to be cautious here because it's not very clear whether it's not very clear how the unfinished vehicles are counted here. So when some vehicles are not completely finished because they are missing some ECUs, some chips, they may be counted as produced vehicles. So we need to be careful here with the way we follow the announcement in China. On overall, I think it's important to listen to the chip makers themselves here on how they see it. And this is what we show on the left slide here, on the left of the slide. Infineon and NXP are the number 1 and 2 chip makers today for automotive, and both of them are still very cautious. The CEO of Infineon announced here on the latest earnings calls that they see supply limitation well into 2022. And then NXP also said that this imbalance of supply demand is not going to be over this year. And then overall, we see that the supply chain remains very fragile. So I already mentioned that some of the OEM, few weeks after making very optimistic announcement, were cutting this forecast. And we've seen that for several reasons. So floods in Malaysia, end of December, for example, have affected back-end plants again. This has affected Toyota, for instance. We see as well some shortage on the substrate for packaging the chips. And we see some microcontroller suppliers already affected here. So one microcontroller alone already announced that they will not be able to deliver 900,000 parts here in February, March. So this is massive. This will contribute to vehicle loss of hundreds of thousands of vehicles here. And then we need to also be careful with Ukraine invasion, because majority of the gas needed for the fabrication of some of the mature chips is coming from Ukraine today. So overall, yes, we see some very optimistic announcement, but we want to call for caution here. The supply chain remains fragile. And I think one impartial indicator here, which one should look, is the evolution of a lead time for automotive chips. So we have developed an index to track the evolution of the lead time here, which means the time one tier 1 or one OEM needs to wait from the time it places an order until the chips are delivered. And we show with the 1 here the long-term average, which used to be typically around 12 to 16 weeks here. And you see how since October, so before the whole crisis really started, it has really increased significantly. And we are here at 3.5 times higher. So it means right now, the lead time is about 52 weeks, is about 1 year, as opposed to 3 to 4 months before. So yes, the lead time looks like it's flattening. It's not growing anymore, or not growing as fast, but it's still very, very high. So it's a very strong indicator that we are far from being back to normal. So this is our view, but now I would be interested in your view on when do you think the constraints on the car chips will be completely over. So you can, we propose that you answer here. You can choose any of these answers. So second half of this year, first half of next year, second half of 2023, 24, 25, or never, because it's the new normal. So I would encourage you here to answer here online, and I will show the results. Give you a few more seconds here. I got a third of the attendees have submitted. All right, we are over half, so I will move to the next slides. Okay, so that's interesting. So it's quite balanced. It's interesting. So very few people expect that it will be over in the second half of this year. Okay, so overall, this audience here is in line with what we think. About a third here thinks the first half of next year, the second half of next year, and still a fourth thinks it's not going to get back to normal before 2024. So overall, an audience which is actually very cautious, like we are as well. So thanks for this wisdom of a crowd. So I would like to show how now we believe that it's going to get better. It has already started to get better, and I'd like to show it with numbers why we believe it's going to get better. So this slide is a little bit complex, but I will explain it. So you can see here with the orange line, this is the actual. So this is the number of chips produced for automotive. So we've taken one type of chips which is representative, the analog chips, and these are the chips. This is the production reported by the chip maker. So these are real number in orange since 2017. And what we have in gray here is the calculated demand. So it means it's based on the vehicle production, which is above. This is the number of chips which are needed for all of these cars produced. And as you can see, while the two lines are very well aligned here from early 2017 until end of 2020, this here, the two lines are diverging massively here when the allocation crisis started. While as you can see, while the gray line, so the theoretical demand or calculated demand goes down because the vehicle production goes down, the total number of chips produced stays flat. So what we see here is that the chip vendors have still produced at the maximum capacity all through 2021, despite the fact that the car production was going down. So part of it is due to inflated orders, but overall there hasn't been a drop of the chip production last year, contrary to what one would think. And then what it means here is that there has been an overshoot of chips production here, which we are showing in this orange area, because all of these chips here have not been consumed. So it's quite counterintuitive here to understand there was more chips produced than needed last year when all we were talking about was shortage of chip. But we need to understand a lot of these chips were stuck in the production chain. So for example, if one electronic system needs 50 chips, and if one of these chips is missing, the other 49 chips have still been produced, and only a share of it may be allocated to other systems here. So this is when there is a mismatch of production and demand here, it's very inefficient, and a lot of chips are somehow lost in the process. And you may have heard as well of seeing these pictures of parking lots where OEMs were parking hundreds of thousands of vehicles waiting for one final system or one ECU to be completed, waiting for one or two chips. So it means if a vehicle consumed 1,500 chips, most of these chips were already produced in the vehicles, but they were not counted as vehicle produced. So this is where this mismatch of production is landing. But what we see here, and this is why we are more optimistic, is we see that the industry, the car makers have started to absorb this overshoot of chip production. We've seen the car production has gone up significantly in the last quarter of 2021. And then what we'll see also is that this mismatch is actually getting resolved. So it means the chip production is starting to be much better aligned with the real demand based on car production. So this toilet paper, this panic buying is actually starting to resolve, and it's a very good news here, because when there is nothing worse than a misaligned demand on supply here. And then the last reason why we think it's going to get better is that, as you can see here, while the chip production was very flat here all through 2020, 2021, it has started to go up here at the second in the last quarter of 2021, as we were expecting. And the reason for that is that the back-end issues in Southeast Asia here have been solved, but more importantly, a lot of the investment in new equipment on existing chip production lines, which have been decided end of 2020, when the first sign of a crisis were coming. These have taken about a year to produce results, and then it means that it generates additional capacity here for the chip production, which we start seeing up here finally. So altogether, we see the chip supply constraints will ease somewhat through 2022. First, the lead time stopped increasing, as I showed in the previous section. We see a backlog of chips coming through because of the back-end issues in Southeast Asia are finished. So there is some chips coming through the production line here. And then we also see that some of the partially assembled ECUs on cars are also finishing their assembly process and are being counted as vehicle produced here. And then finally, this overshoot of chip production is being absorbed. We also see that the chip production is better aligned with the car production, so the end of this toilet paper effect, or an easing of that, which is very good news. And then finally, some improvement on the capacity because of the expansion of existing fabs, which have been decided in 2020, start to generate additional capacity since end of 2021. And then I didn't mention it before, but also TSMC, the #1 foundry for the chip production, has also committed to increase allocation to automotive in its capacity in the second half of this year. So it means the second half of this year will have a bigger share of the overall chip capacity, which will be coming to automotive. The good news for the second half of the year. So these are the good news, but I really would like to bring a note of caution here for 23 on early 24. We still see a structural supply constraint here, which will persist, not for every chip categories, but for some chip categories through 2024. And I'm going to start here with a result of our analysis here, and then I will explain how we came to this conclusion. So what you can see here is the quarterly vehicle production here historically, so also, again, back to 2017, going down here during the first phase of the COVID crisis, going up again, going down here because of a chip shortage, going up again end of 2021. And on what we are showing here with dotted line is our projection for the total number of cars you can produce based on the available capacity for analog chips, which are one of the major bottlenecks today. So what it means here, we believe that, what it means here is we believe that the maximum number of chips based on the existing known capacity is going to peak around 25 million cars in a positive scenarios here based on how many chips can be allocated to automotive here. And in the worst scenarios, it's actually going down. So let me show you how we came to this conclusion. So how many cars will the fab capacity allow to build in 22, 23 and beyond? So in order to answer these questions, we have built a model which takes into consideration the various elements which have an impact on this answer. So first, you need to understand how many chips are needed per car, especially for those which are a potential bottleneck, like microcontrollers, analog, etc. Then you need also to understand the mismatch of production of demand, this toilet paper effect, which is inflating the issue here. You also need to understand what's the total capacity for the chip production, so based on the capex investments, so the investment in new fabs or in new equipment, based on the miniaturization of chips here, which means you can do more chips on one wafer. And then you need also to understand how much of this global capacity is coming to automotive. how much of it is actually taken by other industries like mobile phones, what's the priority given by the chip suppliers to automotive versus Apple and others, and then it can be also results of political pressure. So we already discussed the mismatch of a production and demand, which is actually getting solved now. But now I would like to go over the other three, starting with the number of chips per car. So on this slide, we are showing actuals here, so real data based on semiconductor production data reported here back to 2022. So we looked at a very long historical trend, and we divided this number by the monthly vehicle production. And as you can see here, the number of chips per car has increased relatively slowly here at the beginning, but then there has been an inflection point around 2016, and the number of chips per car is increasing much faster here in the last 3-4 years. And this explains a question which we've been asked many times here. How could the industry hardly produce enough chips for 77 million cars in 2021 when there was no problem to produce chips for 95 million cars in 2027? And the reason is here. It's because the number of chips per car has increased significantly. And these 77 million cars have consumed many more chips than these 95 million cars here 4 years ago. And this is why here, this is one of the main reasons why there has been this disruption here in the supply chain. So in order to understand why this number of chips is increasing, we need to understand the evolution of the vehicle mix and how it has an impact on the typical chip content in cars. So again, here looking at MCUs and analog, which are two of the main chip categories which have been a bottleneck until now. What we've done here is we have looked at the distribution of a chip content by type of car. So by vehicle segments, so as you move from A to D to E, so obviously the number of chips is increasing as you go to an A segment to a D or E segment. But we've also looked along the vertical axis as you move from an ICE car, so an internal combustion engine, to an electric car. As you can see, there is a massive increase of the number of chips you need. And we all know there is a very fast transition to electric car from 8% in 2019 of electric or hybrid cars to 25% here this year or next year. So this has a massive impact, as you can see from this graph, on the demand for chips. And it's true for microcontrollers, it's even more true for analog chips. If you take a C segment car, for example, here there are more than twice as many analog chips in an electric version of this car than in an ICE version of this car. And it's not only for the propulsion system, it's not only for the inverter, the DC-DC converter, etc. It's also because an electric car typically will be more techy, will be loaded with many more features for infotainment, for autonomous driving, which are consuming a lot of chips. And this is why the electrification actually really accelerates the demand for chips. So we've been talking about various types of chips. It's really important we also understand which chips are going to be more of an issue going forward. And here I'm using again here this lead time chart to give us a glimpse here on how the issues by chip types are evolving. So if you're looking at the first half of the crisis last year, the lead time has increased much faster for microcontrollers at the beginning. And there were really, most of the issues reported were down to microcontrollers. However, as we are looking towards today, the lead time for analog has increased just as much as MCU. So we are seeing that actually analog is one type of components we need to really look more closely right now here. And let me explain why we think analogs may be also the bottleneck. So what we are showing here is a similar chart as before with the average number of chips per car, but then I made the difference here between analog chips in green and then microcontrollers in gray. And typically you need a few tens of microcontrollers in a car, but you need hundreds of analog chips per car. So you need many more analog chips. And then also what you see here is the trend, the increase for analog has been much stronger. And it's really important to understand, even if everybody is talking about a digital car, a car is still very much in contact with the road and with the real world. So you need analog chips for every type of electronic system in a car. You need analog chips for the power management of every electronic system. For every sensor needs some analog circuitry as well. Also, the in-vehicle network needs analogs. Every bus transceiver is an analog chip. And then also, you have in an S-Class, you may have 100 electric motors for all of the seat electronics, the roof, all of these comfort functions. And all of these motors and all of the LEDs you have in a car needs an analog driver as well. And then also the radar transceiver. So there is really a boom of the demand for these analog chips, which you can see here, and which is not going to go down. So we've seen here the number of chips per car really increasing very fast as one of the input to the model to understand how many cars you can build here in 22, 23, etc. Now the next part we need to look at is the total capacity for chip fabrication. And before we talk about capacity, one need to make a step back and understand there are many types of chips, and many types of chips fabricated on various types of processes. So you actually need to go more in the detail of which process for each chip to talk about, to analyze the capacity for various types of chips. And this is what I've tried to explain on this chart here. So it's a little bit complex, but I will explain. So we've shown here the various type of chips, or the main categories, so microcontrollers, SoCs, so the powerful processors here you need in a car, the analog chips, memory, etc. And I ordered them here by process technology, which are going from 800 nanometers. So this is the precision of the resolution of the etching process for etching the circuits here. And it used to be in the micrometer business area. In 2000 we were talking about 180 nanometers, and now we are going down to 3 nanometers on lower. So as the industry evolves here, we are using more advanced, smaller process nodes. But as you can see here, a lot of chips needed in cars, we are talking about hundreds of analog chips, tens of MCUs, etc., tens of power discretes, are using still very old technology, as you can see, which have been deployed 10, 15, 20 or more years. So, and what's important to understand is that these rather mature process nodes are not only needed for automotive, they are also in increasing demand also for mobile phones, which are, as you know, needed in very big volume. So you need more and more analog chips as well for mobile phones, also for power management, for all of the RF front end, for the high-end audio, etc. And this is really where we see an issue here in the future because of this competing demand of mobile phones. And especially if you're looking at the investment which has been done to increase the capacity. So these are numbers here from the SEMI Association, so official numbers. And as you can see here, the vast majority of the investment here has been done on the more advanced processes, 28 nanometers on smaller, 86% here for 21 and 22. And only a fraction of investment has been done on the more mature process technologies, although these are required for more than 90% of the chips in cars. And this is why we see here this capacity crunch in the years to come on automotive for process nodes, because there is not enough investment, and because there is an increasing demand from other industries as well. And I just noticed this comment from the CEO of Apple, which are actually also commenting on this, saying that most of the investment for chips has been on the most expensive chips, so the 3 nanometers. But he as well is worried about the supply constraints on the legacy nodes. So if Apple, who is king of a supply chain, is worried, automotive industry should be worried as well, because they are depending even more on these process nodes. Okay, so we've seen that the capacity in terms of wafers is not going to increase as much as it should. So one question we need to look at, can we make the best out of it, and can we stretch the number of chips we can produce on this existing capacity here as we shrink, for example, the size of the chips? So yes, this is true to some extent, and we've been calculating here the trend here to increase the number of chips you can produce on a wafer over the last few years. And this is what we are showing here. So we are showing that in average here since 2014, this is a trend line since 2014. Every quarter, the number of analog chips you produce, or which has been produced on a given wafer capacity on an equivalent 200 millimeter wafer, has increased 2 quarters per quarter since 2014. So this is an interesting number. And the reason for this is a gradual transition, a slow transition to smaller process nodes from 360 to 180 nanometers to 90 nanometers, for example, for analog, and also a general productivity increase. What we've seen as well is a burst of this increase of capacity in the second and third quarter of 2021. And it's not very surprising, because we've seen exactly the same in 2010 after the financial crisis, during the allocation crisis, and when the industry was trying to catch up with this pent-up demand here. So there is what has happened here is a so-called hot lot mode here, when the fabs say they are working at 150% capacity. So what happens here is there is a surge of demand, and the fabs are trying all they can to just answer this demand. So they are reducing the downtime as much as they can. They are moving manually the lots from one station to the other, reducing the downtime. They are even pushing out maintenance cycles for a while, just to be able to produce during a short period more chips. But this is over. This, as you can see here, just like in 2010, this has lasted just 2 quarters, Q2 and Q3 last year, and it has come down closer to the normal here. And the reason for that is that running this hot lot is very disruptive, and it cannot be sustained in a very long term. So therefore, here it has come down. And then looking forward, what we see here is we believe it's going down a little bit further in the next couple of quarters towards the historical average. But the good news here is that, talking to a lot of the analog chip makers, we see that because of the limited capacity on the most mature process nodes, like 300 nanometers or above, we see that they accelerate for new designs their transition to smaller process nodes. So from 300 to 180 nanometers, or from 180 to 90 nanometers. So they're still staying within the legacy nodes. They're not going to go to 40 or 28 nanometers, but it does mean that there is a little bit of an increase of the number of chips you can produce here, starting probably from 2023. So that's the good news here, where we see a little bit more chips coming through per equivalent wafer capacity. So we've seen the number of chips per car, we've seen the total capacity for chip production. Then the next point, which we need to explain here as input to our model, is the allocation of the global chip production capacity to automotive. And for this as well, I thought it would be useful to look at the historical trend here. So what we show here is the historical trend all the way back to 2011 of the share of a global analog chip production to automotive. So as you can see, it has been increasing steadily, but it has really never been more than 10% here. The historical peak was in first quarter of 2019 at 10.1%. You also interestingly can see this drop here in mid of 2020, and this is when the automotive OEMs and tier ones have dropped their order, and then this is when actually the allocation crisis started, because they landed in the back of a queue, while the mobile phones industry, gaming, etc., were still ordering chips. So here you see this is when automotive lost some shares. So going forward, the good news we see is that we expect actually in the second half of 2022, we see a surge, we see an historical peak of the allocation of this global analog chip capacity to automotive. And this is based on the some of the communication of TSMC, which says they will be able to increase the allocation to automotive. And it's not because they love automotive more than others, but it's mostly because we've seen some slowing down of some other industries here, which means they can actually allocate more to automotive. We don't expect it will remain at this very high historic peak. We expect it will come down to normal here. So this is what you see here in the more from 23, probably going back to the closer to this trend line evolution. And these are the various components here at a high level, which are built into this model, and which show that we, in a positive scenario, we expect that the maximum level will plateau around 25 million cars per quarter, which means here that we cannot actually serve a pent-up demand beyond 100 million cars as we were first thinking. There is the global demand for car is beyond this level, but there will be still constraints going forward with the available data as of today. And what you can see here, it's even in the positive scenario, it's plateauing. In a negative scenario, it's actually starting to go down. It's because while the capacity is increasing, it's not increasing as fast as the demand for analog chips in average per car. So this is the problem we are seeing in the long term here. We don't see really an increase of the total capacity in terms of number of cars which can be produced. And here, what we can see here is we have overlaid the vehicle productions here. So this is the February vehicle production. And it's now our vehicle production analyst is using this as a guidance. And this is actually staying here between these two scenarios, as you can see here. But I would like to issue a note of caution on this model. This is a model. This is not perfect science, obviously. And this becomes more or less robust or more risky in the second half of 2023 here. It's also based on the known capacity on investment as of February 2022. We hope there will be some positive announcement on this, that this ceiling will go up a little bit. And finally, we know that there has been a lot of announcement, a lot of fabs, new fabs from ground have started to be produced here around the world. It takes several years until, from the moment you start a new fab until it produces really a new capacity. So it will possibly, we expect it will lift up this ceiling here in 24 and 25. But again, through early 24 here, we see a risk here that the total capacity will still be constrained here. Okay, so we see for the foreseeable future, the capacity will be constraints. And what we are also seeing is that the OEMs are getting ready for that. And I'd like to go through some of the strategies we've seen here to deal with this new normal. So the first one is decontenting. So we all have read reports here last year of removing some features just to be able to build the car because the chips were not there. So we've seen more cars shipping with a all-styled analog speedometer, for example, cars removing wireless charging, head-up display functions, etc., or some ADAS features like surround view parking. But last year, it was really a reactive mode. what we are wondering if, as the industry wants to build more cars in future, whether they will have a more proactive strategy to carefully select which features they will open in cars so that they will still be able to produce the number of cars they want. The question here we need to ask ourselves is which feature may be sacrificed without losing customers. It means which comfort features may be compromised on, which are consuming a lot of analog chips or MCUs, but which you can remove without losing the customer. So it's not easy. We've been looking at the typical content in cars. On one which stands out as an example is the seat comfort electronics. And here are a few examples. So it's an extreme example, Mercedes S-Class. You can't do much more here, but we counted 34 analog chips on 9 MCUs, 9 microcontrollers, just for the seat comfort electronics. So that's a lot of chips you could possibly allocate to other ECUs here if you were not offering all of that. So I would be again interested in your opinion on that, because it's a little bit difficult for us to know which features will be removed. So I would encourage to give us your opinion here. Which features are consumers ready to sacrifice so that they still can buy the car they want? And you can select as many options as you want. So I will give you a few seconds to answer these questions here. So we'll see the results of this survey in a couple of slides, and then I'm going to move to the next slide. Okay, so another strategy we see here, which is very, very interesting, is possibly simplify the chip content on having more multi-purpose chips in cars. So today, we really have a hyper specialization or customization of chips. There are a lot of chips in a car which are used or built for a very unique application. So you will have a so-called application-specific IC here, ASIC or ASSP, just for active suspension or just for ABS. And it means if you remove this, you cannot reallocate to another ECU. And even the standard chips are very fragmented. You know, a microcontroller is very standard, but even when you want to select a chip, for example, the 32-bit Oryx TC2XX family from Infineon, the OEM will have to choose, or the tier one, between 6 types of flash, between 3 types of frequency, between single, dual, triple core, and 2 different temperature range. So it means there is a really high fragmentation of the offer of the supply of chips, which is actually exposing the OEMs. And what we see going forward is more multi-purpose chips to be more flexible, so that if you remove one optional ECU, you can reallocate these chips to other ECUs to build more cars. To be also less exposed, you know, every of these unique chip is a single point of failure. And then also interesting, the more volume you have per chips, the higher priority we have with chip suppliers. So GM has made an announcement in November going in this direction, which is very interesting. And they are very, their statement is very, let's say, optimistic here. They say that they will reduce the variety of MCUs by 95% on their future vehicles with this kind of approach. So it's a very interesting approach. It's not only GM. We already discussed it with some European OEM as early as the summer last year. So we expect this kind of strategy to be more to be adopted more globally in the industry. And then in the long term, we are also believing the move to new E-architecture, so more centralized computing, will also help to that extent. You may have heard of some announcement by Tesla, which has actually survive this crisis better than others. And you can see here with a real example the impact of the centralization of a move to new architecture. So the Tesla Model S, which was built on a classic architecture, was using 75 to 80 microcontrollers. The Tesla Model Y, which is using one of the very first car using this centralized architecture, is using only 20 MCUs. So Tesla has been able to cut by 4 the number of microcontrollers with this move to new architecture. This is interesting, again, for microcontrollers. We don't think it will have an impact on the demand for analog. So it's not the solution to everyone, but it will help. Okay, so now we are seeing the results of the answer here. So which features you believe consumer may be able to sacrifice so that they still can buy the car or they want. So more infotainment features, so wireless head-up display, so that's interesting. Comfort electronics like seat, electronic sunroof, lighting. And interestingly, we were wondering if some of these basic ADAS function would be sacrificed, but apparently not. Okay, so thank you everyone. That's a very interesting results here. Okay, so we have not so much time, so I'd like to go now into the last part of our presentation about the impact of a war in Ukraine. So you may have read some articles here pointing out that 70% of the global supply of neon, a gas you need for some chips fabrication, is coming from Ukraine. So yes, this is a concern, especially as neon is required for these mature chips, which are already under pressure. But we don't expect this will have a major impact on the supply of chips. We know that there are alternative suppliers from Japan, from South Africa, etc. And the price of neon gas will increase, but we don't believe there will be a major disruption on top of the existing problems here for chips due to this crisis. However, there will be definitely impact on the car production because of other type of components, and especially wiring harness. So we just published an analysis here showing which type of components are actually produced in Ukraine, and we see the wiring harness being very, very difficult to relocate. So there will be cut to our vehicle production forecast. Our vehicle production team here is working on this, and we see the German OEMs are going to be more exposed, especially to the wiring harness disruption. But the next question we asked ourselves here is, as we cut the global car production in 22 and 23 because of a disruption here for wiring harness, as we move down the vehicle produced, will it somehow ease the constraint on chips? Actually, we don't think so. And the reason for that is that the wiring harness disruption is very OEM specific. It's not a global widespread issue. On the OEM which are affected, they have learned from the past crisis. They've learned from the COVID, the beginning of the COVID crisis, when they reduced their orders and then they landed at the end of a chip queue here. And they certainly won't make this mistake again. And we believe that the OEMs actually are going to maintain their orders just to make sure they are ready to bounce back when the wiring harness supply is solved. And then what could have an impact is more the vehicle produced in Russia and Ukraine. So it's about 1.5 million vehicles. If the vehicle production is revised downward in the midterm for this, then it will somehow reduce the global demand for chips. But here it's too early here to make a prediction on that. So that leads us to our final slide here. And so what we see is the light vehicle market will remain constrained by the chip supply through 2024. Yes, we see that the situation will get better in 22 because of some capacity expansion on existing fabs, because the allocation towards automotive will increase in the second half of 2022, especially at TSMC, and also because we see that this misalignment of chip production and car production is actually reducing. So that's a good news. But we think that after microcontrollers in 21, analogs are likely to be the main constraints in the next 3 years. First, because we see the number of analog chips is increasing faster than MCUs, that there is a high demand for analog outside of automotive for mobile phones, and there is not enough investment on these mature technology nodes here. We see that the OEMs are exploring various strategies from short to long term to deal with this new normal here, with this chip supply constraint. And then we also see that the Ukraine crisis is actually, we don't think it will change too much to this chip issue. So that's one comment we wanted to make here as well. Okay, so thank you for your attention, and I will let Mohit take over now.
Thank you, Jeremy. What a lovely presentation, especially around insights around analog chips as a bottleneck, consistent increase of semiconductor that goes into a car, which has almost doubled from 2017 to 2021, semiconductor manufacturing process nodes, features sacrificing what OEMs were thinking in 2021, and of course the Ukraine-Russia conflict. Now, probably I'll move it from here to some questions that we have received, and the numbers are quite high. Considering the importance of this topic. Due to paucity of time, we will take a few questions now, and the remaining ones, all of them which are unanswered, we will reach out to you via email, and we'll answer each one of them. So here it goes, the first one. In the beginning of your presentation, Jeremy, you mentioned that US has seemed to be impacted more. Can you throw some light why?
Okay, I think, let me go back to the slide then to comment on this. So it's true on this slide. It looks like, and it is true, North America has been impacted more, especially in the second and the third quarter. So I think maybe rather than explaining why North America has been impacted more, I would rather comment on on what has helped the other regions on which we have not seen in America. So if I start with Europe, we've seen in Europe some of the German premium brands had a really deep understanding of the semiconductor chain, of their supply chain, much better than the rest of the world here. I would say, for example, BMW stands out here with a huge team dedicated to understand their supply chain before all of these supply issues started. So that helped them actually to work with their suppliers earlier on, anticipate a little bit better. So that's one reason. What we also see in Europe, also again, more from the German premium brands, we've seen that they've been sometimes paying more for the chips to get in front of the queue. And for this reason, they've been able to deal a little bit, to be a little bit less affected because they've been ready to pay a higher price for the chips to get these chips. If you're looking at China, it's similar to what I just said for the European premium China for the price. We've seen the price paid by China for chips was actually much higher than the rest of the world. So we've seen that they also here have tried to come in front of the line to get the chips they needed. We've heard some reports, anecdotal reports, of chips which were paid 5 to 10 times the market price just to make sure they get the price. So I think that's one reason why China got a little bit better. Japan and Korea, it's a little bit different. Both of them were actually better prepared for a disruption of chips. Korea, we know that Korea had started to build more inventory in 2019 already because of a tariff trade war here. And for this reason, when the crisis started, they had a little bit more of a buffer of chips, which made that they were, at least for the first half of the crisis, better equipped here. Then at some point, this buffer was consumed and they were affected like the rest. And Japan is also similar. The Japanese conglomerate here are, they are very tight. They are integrating the chip suppliers in the groups, like Renesas have financial ties to Denso and to Toyota. So for this reason, they were able to have more inventory. So typically 3-4 months of inventory last year before the crisis started, which helped them actually to navigate the beginning of the crisis much better. And again, at some point, this inventory has shrinked and they were just affected as everyone else. So I would say this is why probably Europe, China, and Japan and Korea look a little bit better than North America, because we don't see any of these actions I just mentioned really haven't been taken, as far as I know, with the big North American OEMs.
Understood. Thanks, Jeremy. All right, moving on. We'll take a few more questions, though we are bang on time now. We'll extend this webinar by a few minutes in order to take a few more questions. There's another one, interesting one, which has come is, can you please explain the mismatch in investment between older technology and demand? Why has it occurred?
So first, there is more money to be made on a very expensive processor. If you're looking at the latest NVIDIA processor or Qualcomm processor for infotainment on 7 or 5 nanometer, you will be able to sell it for $50, $70, $100, as opposed to an analog chip. A simple, voltage reference will be, just a few tens of cents. So I think there is just a question of margin, which is higher probably on some of the more processed nodes, which is an incentive for the OEMs not for the OEM, for the chip manufacturers or for the foundries to put more of their investment in these more mature. Then there is actually sometimes an issue of just the availability of the equipment. Through all of the 2 years, 2010 to 2020, as some of the chip technology were moving to smaller process nodes, a lot of existing equipment has been refurbished, and this has helped the production on analog, discrete, etc., the more traditional ones, to keep expanding the production. But there hasn't been as much anymore equipment built on this 200 millimeter wafer size, for example. All of the new equipment is on 300 millimeter now for the more advanced, and it's sometimes even difficult to buy the equipment. So that's another issue. And then I think one problem is I think sometimes down to the politics. You may have seen this huge investment recently from the European Commission, the European Chip Act, I think 48 billion euro, which is great, to support the European chip production. Something similar in the US, here around $50 billion. The problem with that is the vast majority of this is, again, on what appears to be strategic. And I think for a lot of this political incentive, it's making more sense to concentrate it on the most leading edge. It's more sensible from a strategic point of view to make sure you have the leading edge technology, the 5, 3, 2 nanometers. This investment in the US a little bit more, but in Europe haven't been made thinking of what's the industrial needs in terms of capacity. So we see here the further investment triggered by politics are actually not helping. They are still going even more towards the advanced process nodes rather than the old one. But again, the main reason I think here is these analog chips are fairly cheap, and it's more, there is less of a financial incentive. There is more of a fear for return on investment to invest a lot of money to build additional capacity on chips which are fairly cheap here, fairly inexpensive.
Got it. Thanks, Jeremy. And one more question, a very interesting one. Some OEMs say that they are going to design the chips themselves. Is it a solution? Is it a long-term solution? And do you see a trend here?
It's not a solution for every chip in a car, and it's not completely new. I mean, there have been announcements back to, or if you're looking at Tesla, for example, they have already designed their processor for the autonomous driving box, for the autopilot's control box themselves for a couple of years. And we see Volkswagen having announced the same. They are actually designing themselves their processor for autonomous driving. So this is something we've seen independently of this chip crisis, but more for the very, very strategic chip, which are enabling autonomous driving on it, which enabling you to differentiate. What is really new here is that we start seeing this also for more not as advanced chips. We see, for example, Hyundai really working how they can design themselves on really control the chip design on production for not for this advanced processor, but for discrete chips, which are needed more for the control or for operating the electric motor, so more associated to electric propulsion here. So these are fairly old process nodes here. These are not the leading edge, but we start seeing here some OEM doing that. And again, it's because electrification is strategic and they want to make sure they are not hampered in their future plan to grow here. So we start seeing that. And I think the most important is more what I mentioned with the example of GM here, which is not the only one, is maybe not designing themselves, but being more involved in their supply chain, in the type of chips which the tier one are going to use, so that there is less hyper specialized chip, which you can only use for one ECU, and there are more multi-purpose chips, which gives you a lot more flexibility. So I think the majority of the redesign here will be involvement of OEMs in the type of chips, making sure it's less fragmented, it's more scale on more multi-purpose reusable chips across a variety of functions. I think this is the future here.
Okay, understood. On a lighter note, Jeremy, I think we have 60 emails to respond now.
Okay.
Right, so we'll break the question and answers right now. Thank you everyone for attending today. Here is our upcoming webinar on 5th of April 2022, 9 a.m. GMT for 1 hour. The topic of the webinar is Global EV Charging Outlook. We have speakers, Tanya Lincoln, who is an Executive Director for D&D, Automotive D&D. We have Claudio Vittori, who is Senior Technical Research Analyst, Powertrain and Electric Mobility. We have Anup Desai as Director, Automotive Advisory Services with S&P Global. You may want to register with this code here. Thank you. Thank you everyone for attending.
There are over 1.5 billion vehicles on the road today that all have something in common: the essential intelligence of S&P Global Mobility. We provide invaluable information across the entire value chain, enabling vehicle manufacturers,